And we are live. Hi, ast111x. This is the first of two YouTube live events that we'll be doing. We'll do another one in about 3-4 weeks or so. And I can't be having another audio source going home. So my name is Frank. I'm the instructor in the course, and research-wise, I guess one way to say it is I like to blow things up, both for the fireworks they make and for the elements they make. And I'm a professor here at Arizona State University. And with us we have Tom and Alex. So Tom, why don't you start and say a little bit.
Hi, my name is Tom Mosden. I'm a graduate student at Arizona State University. I went back to school after a career as an electrical engineer, and now I'm studying the early universe through the radiation that the early hydrogen gave off when it was neutral. Gives off a faint glow and a 21 centimeter radiation, and we're looking at that radiation to try and determine when the first stars formed and how fast they formed, which eventually ionizes that radiation and changes that 21 centimeter signal. So we're trying to figure out when the universe went from a neutral hydrogen interstellar or intergalactic media to a fully ionized media that we see today. Alex?
Hi, I'm Alex. Like Tom, I also work here in the School of Earth and Space Exploration, and I'm also a PhD student. I'm actually in my lab right now. In our lab, our research focuses on building camera payloads for suborbital and orbital missions. So we've worked on balloons, we've worked on sounding rockets, and now we're currently working on a couple CubeSats. So it's a lot of fun to get some hands-on experience with space hardware. So that's kind of what I'm doing, and I'm in my fourth year, or just finishing up my fourth year here.
Cool. Okay, so one thing we're going to do is we'll answer some of the questions that are posted on the discussion board. You're free to get in there and still ask some questions. There's also a chat window. If you feel like asking your questions there, we can take those questions from the chat window if you like. So I'll start off, and one of the questions that's in the discussion board is from Alejandro PB, which was, how could the two basic elements of the Big Bang, hydrogen, helium, because that's what the Big Bang makes, had originated all the elements of the periodic table? And that's a good question. How do you start from a couple of colorless, odorless gases and at the end out pop people? And that magic happens in stars. Stars burn fuel. They start off burning hydrogen, just like the sun is doing right now. So they burn hydrogen, and they burn that into the next heavier fuel, which in this case would be helium. And so this is what the sun will do. It's currently burning hydrogen. It will burn it to helium. And then after a while, the hydrogen fuel runs out. So you run out of gas, so to speak. And then in stars like the sun, the next fuel lights, and you burn helium into carbon. And for stars like the sun, that's kind of where the burning stops. So you'll end up with a carbon ball at the end with hydrogen, helium given off. In stars more massive, because they're more massive, the temperature gets hotter in the inside, and that process of fuel to ash and that ash becoming a new fuel can repeat itself. And so you burn helium into carbon, carbon into oxygen, oxygen into silicon, silicon into iron, and that is how you essentially produce most of the periodic table all the way up to iron. Then in the process, when those more massive stars explode as supernovae, as Tom mentioned in his answer, you can make elements that are heavier than iron. So you can make the gold, the tin, the silver, the uranium, all that kind of stuff is produced during the explosion. So basically it's stars that are the element factories of the universe, and they do that by converting one element into another, and in the process releasing energy that we see as the light from the star, or the light from fireworks from the explosion. Okay, so that's that one. And Tom, you want to take one?
Sure. There was a question about assuming that the universe started with a big bang, then we can reasonably assume that there might be other Earths in other parts of the universe because material or the universe expanded uniformly, sort of, and galaxies and other solar systems are to be found throughout the universe. That's definitely true. Recently, some exoplanet searches have found candidates that look like they could be very similar to our own Earth. And for a good read on this subject, our own Paul Davies at Arizona State University has written a book called The Eerie Silence, meaning there should be lots of these planets out there with life developing on them. But the eerie part is that why haven't we heard from any of these people yet? And I highly recommend that book. It's not a technical hard read, but it's very interesting, and you'll have plenty of items to reflect on. Okay.
Okay, I'll take the third question. It's probably easier to share my screen here. So this is from Odd Geir Hoyland. I hope I pronounced that right. But when the Earth is closing in on a perihelion in its orbit, so if you remember, perihelion is when the Earth is closest to the sun in its orbit, Earth's velocity and centripetal acceleration rises. If you're in a car doing a tight turn at speed, you will feel a force pushing you to one side of your seat. Are these two situations comparable in any way? Does the, quote, tight curve of Earth's orbit in perihelion affect its mass in any way? Like, for an example, giving a measurable effect to tides. So the way that I would answer this is just conceptually. This is a kind of a cool question because you're thinking about actual physics. Conceptually, though, I would say think about the classic example is flying in a plane, and planes travel about 550 miles per hour, pretty fast. But you can get out of your seat in a plane and go to the bathroom, and you're not going to fly back and hit the back of the cabin, right? So when you match inertia with the object that you're on, you essentially don't feel that movement anymore. So it's kind of the same situation here on Earth. So while we are going through a curve in our orbit, it takes us 365 days to go in that big circle around the sun. And so you say that you're taking a tight turn in the orbit, but it's actually an extremely smooth, very, very, very small measurable force as we're going through that orbit. So you don't really feel it. And Earth's orbit, it is elliptical, but it's a very circular orbit. So we're not going through parts of Earth's orbit that are way faster than other parts of, than from the apogee to the perihelion. So I hope that answers your question. Okay.
Okay, why don't we go one more round of questions, and then we'll do a couple of presentations. So I will take the question from Dove MT, since it kind of relates to the question I answered earlier. And it is, could there be new elements found in other galaxies that do not exist in our solar system or galaxy? And do people suspect that there are stars in other galaxies that would provide an addition to the periodic table as we know it? Thanks, Michelle. Short answer for that is no, the periodic table is the periodic table. And we know that because when we take that starlight or that light from galaxies and we break it down into its rainbow of colors, which is something we'll learn about next week, I believe, when we start covering the light. So you take the light and you disperse it into its spectrum, you turn it into a rainbow, and you can identify the features in that spectra from each element. And we don't see any features in those rainbows that would be indicative of new elements. So in other words, the process that makes the periodic table is universal. It's the same in our galaxy as it is in other galaxies. So there's not going to be new elements created in other galaxies somewhere. Now we can't extend the periodic table. We can do that here on On Earth, you can make elements heavier than uranium. That is done relatively routinely. And I think, if I remember right, this is off the top of my head, so forgive me if I don't get it quite right, but I believe we're up to about 119 on creating new elements. These things don't last very long. They last on the order of less than 10 to the minus 12 seconds, a picosecond, a femtosecond, 10 to the minus 15 seconds. So they only come into existence for a very fleeting part of time, and then they go away. So why do this? Why keep putting all the energy and effort into making something that's only going to last 10 to the minus 15 seconds, other than to say the fact that you can do it? Well, the idea is that if you get heavy enough, the so-called super heavies, the transuranics, that there's going to be an island of stability out there, somewhere around mass numbers of 140, 150, and for reference, uranium is 92. That it will be an island of stability, and instead of lasting 10 to the minus 15 seconds, they may last forever, that they would be stable elements. And the thought is that those could have some pretty exotic properties that could be useful for whatever properties they may have. They may be naturally superconducting, they may be super elastic, so you can be like rubber band man there. We don't know yet, but that's sort of the hunt, is to keep pushing the mass numbers up. But so far as we know, these are all made in a human laboratory, a terrestrial laboratory. They're not made in stars. Stars sort of end their journey around uranium. Okay, and Tom.
Okay, I'll take the question asking about prevailing challenges to the absolute cosmic speed set by the speed of light. I think the question is asking, is the speed of light constant, and is it possible that we might find it's different in other parts of the universe? I'll just make the comment that the scientists are always open to the possibility that the speed of light might be different, and they're always checking it, but the answer always comes back that it's constant at about 3 times 10 to the 8th meters per second. As an example of this, there's a team from Italy that thought they had discovered a discrepancy in the speed of light and actually published a paper on it because they were so convinced that they couldn't find any errors in their setup, and they thought they needed to report it because if true, then there might be something worthwhile understanding why the speed of light might be different. But after thorough research and checking, alas, the miscalculation error was found, and once again the speed of light prevails as 3 times 10 to the 8th meters per second. But that's a very fundamental constant to all of our physics. So people are on the alert to check any discrepancy because it is so important, and any discrepancy would have massive repercussions. But as of yet, it's stood the test of time, and it always comes up constant.
Okay, I'll take a fairly recent question on the message board, and it's pretty straightforward. Can you please explain the zenith and its purposes? So I thought this was a good tie-in to when you actually go observing, and I have an image here. I don't know if that's showing up properly, but the zenith is essentially the point directly above the observer. So this is different if you're thinking of the Earth's whole coordinate system. It depends on what you're comparing it to. So if your zenith can mean multiple things, like if you're comparing the Earth's coordinate system to the plane of the galaxy, etc. But just for if you're going observing with the telescope, the zenith is typically the spot directly above your observatory, and we usually call that 90 degrees. It's also important to note that in using this coordinate system, essentially what you want to call up-down is what the astronomers call the altitude, and side to side along the horizon is called the azimuth. So you'll hear sometimes telescopes use what are called alt-az systems, and that's just referring to that they can move in these two axes along the north to east to south to west axis, and then up from the horizon all the way up to the zenith and back down. So I hope that answers your question.
Great, thanks. Let's go ahead and move into some of the shorter, we'll do some presentations on some stuff. And I believe Tom is gonna start off. Take it away.
Okay, let's see. I'm screen sharing. All right, is that showing up?
Yes, it is.
All right, thank you. I'm going to talk about how one can get to know the night sky. And that means when you go out in the sky, or you go out at night, outside at night, and you look in the sky, you see all these stars, and how can you come to learn them a little bit better, learn the constellations, know what you're looking at, know what time of year it is by what you're looking at up in the sky, and perhaps point out some constellations to your friends while you're outside. So we'll start out with what you can see using only your eyes, and then what objects are good to look at with binoculars, and then finally what objects require a small telescope. So let's start with the constellations. There's 88 constellations, and they're mostly very large, so that they're best viewed with the naked eye that can take in large portions of the sky. Because a telescope or binoculars gives you a limited field, and you can only see a smaller part of the sky with binoculars or telescopes. And so you can remember how many constellations there are by how many keys on a piano. It's not that important, but 88 and 88, it's easy number to remember. Some are only visible in the northern hemisphere, and some are only visible in the southern hemisphere, and of course some are visible from both locations. And it's definitely easier to identify if you're away from city lights, because then you can see some of the fainter stars, and the patterns that the stars in the constellations make are easier to identify with some of their historic names. And also I'll show you a nice website that will help you look at what you should expect to see overhead at that night. You would type in your location and time, and it will give you a sky map of what you are going to see that night. Alrighty, I'll just go through a short list of these constellations. The ones that are visible from the northern hemisphere, namely in the area of around the latitude of Phoenix, 33 north latitude, up to perhaps the Chicago area in the 40 north latitude. So there's about 52 of them that are easily visible from, say, the Phoenix area, which is quite a few, more than half of them. And I've highlighted the ones that belong to the zodiac in bold, and they're in alphabetical order, not the order you'd see them in the sky. Got Aquarius, for example, Cancer, Capricorn, Gemini. And the ones I've put in red are ones that are harder to see, like Camelopardus, Lacerta, and Lynx are very, very difficult to identify in the sky, because the stars in those constellations are very, very faint. Whereas others are very easy to identify, such as the Big Dipper, or let's see, Leo's another one that's easy to see. And I've also pointed out Ophiuchus. That's one of the constellations that the sun goes through that is not historically counted as part of the 12 constellation zodiac. Anything else? Yeah, if you get a copy of this list, I would suggest printing it out and just go into the night sky and check off the ones that you can identify, and look at sky maps, and do this other times of the year, and see if you can't get get a couple dozen that you can easily recognize. Then moving down to the mid-latitude constellations, there's a set of 18 from the Phoenix area. Some of these are visible, most are not. Suppose if you're on the equator, you could see all of these really easily. Fortunately, the constellation called Phoenix is actually visible from Phoenix, so that's kind of nice. Southern constellations, these I don't know that much about because I've never been to the south of the equator, but from all of the pictures you see of constellations and objects in the south, the southern hemisphere has some of the most amazing objects to view. So if you live south of the equator, please go outside and get some binoculars or a small telescope and view some of these objects that are just completely amazing. And there's a website called Heavens Above, and there's the link on the right. I put the link in the discussion notes. And as you can see, you can stay anonymous. Just give your location and coordinates. I think it's smart enough to figure out where you're dialing in from, and it would use your current time, but you can change the time, change your location, and it'll tell you, it'll give you a sky map like you see right here, and say, oh, you can see Ursa Minor, the Little Dipper, you can see Pegasus, Lyra with the Vega star off to the right. So this is very helpful. This website will also tell you when the International Space Station would be overhead or the Hubble Space Telescope. And it also has a listing of when the Iridium satellites are overhead, which sometimes will reflect the sun and give you a very bright glare for maybe 10 or 15 seconds, and that's quite spectacular. It gets brighter than Venus. So it's a great website to play with and get more information. So now let's take a look at some objects that are best seen with binoculars. M45, otherwise known as the Pleiades or Seven Sisters or Subaru, is awesome in binoculars. They'll fit in the field of view just fine, and you'll see a beautiful set of stars that almost looks like maybe a mini dipper. Then off to the right is called Melat 111. It's a little cluster in Coma Berenices, and there's this nice little shape of stars that almost looks like a trident to me, but it's really cool to look at with binoculars. And then we have the Ptolemy cluster. M7, it's a Messier object, which I'll talk about shortly. Then M44 is a beehive cluster in the middle of the constellation Cancer. And then we have the famous double cluster that's between Pegasus and Cassiopeia. And that's really gorgeous in binoculars. A telescope zooms in too far and you can't get the proper perspective. So let's talk about Charles Messier. He was a comet hunter in the 1700s, and he was looking for comets. And comets move in the sky from night to night, so that's how you can tell it's a comet and not some object stuck on the celestial sphere. And if it didn't move and it was blurry, he didn't want anything to do with it. He didn't want to get confused with it, so he made a list not to look at these objects anymore, because they weren't comets. They consisted, now we know they consisted of diffuse nebula, planetary nebula, which is a star that is violently expelled its outer layers, and you can see a glowing ring around these stars. And there's open clusters, which is a loose gathering of stars, and then there's globular clusters, which is a tight clustering of stars, and of course galaxies. Now most of these guys are best seen with at least a small telescopes. He only had a 10 centimeter telescope, and it wasn't that sharp of an image, and so he couldn't really see those pesky blurs in any detail, which might have converted him from a comet hunter to a deep sky observer. So there is a chart of 110 of these Messier objects. This is a collage of the 110. See upper left, there's a Crab Nebula, M1. Then there's some galaxies in here, Pleiades. There's M57, a Ring Nebula, and these are all best seen, or the most of them are best seen with binoculars, small telescope. Okay, so most of these objects are really spectacular. Some of these examples are the Andromeda Galaxy, the Ring Nebula, planetary nebula, the Orion Nebula, and the M1, the Crab Nebula from the 1044 supernova. So let's take a look at some of these objects in a little more detail. So of course, we have M31, Andromeda Galaxy, which is our sister galaxy, fairly close to us, a few million light years away. And then we have the Ring Nebula, M57. You can see the central star in there, and the star is lighting up these outer layers of hydrogen, helium that it expelled, and they're pretty cool to look at. Then we have the Orion Nebula. That's also amazing. That will show up in binoculars as well, but a telescope is best. And then the Crab Nebula, a recent supernova that is still expanding. Okay, and of course, there's a few that are not quite so spectacular, the least of which is M40, which is just 2 stars. But many people think that was probably just a mistake. He was looking for something else, and that was the only thing in the area, so they listed it. But M73, that's only 4 stars, not so exciting. M29 is not too bad, but it's in a busy area of the sky, and it's like, oh, why is that different than the other clusters? Well, Messier got confused, or not confused, but thought it might be a comet, so made the list. And M39, yeah, once again, not very definitive, as well as M26. A very rich sky background of stars with just a slight overdensity of stars, and enough to maybe tempt the comet hunter to see if that thing moved. Okay, but most of them are quite amazing. Here's one, the Whirlpool Galaxy, consuming another galaxy, and you can actually see that in a telescope. And here's an example of a globular cluster, which are some of my favorites. It looks like somebody took a dash of salt and dropped it, a pinch of salt, and dropped it on a table, and those are your stars. They're all fairly close together and very old objects. This one is M13 in the constellation of Hercules. And once again, here's a few links to Charles Messier and the Messier objects, and that's also I put that link in the discussion notes for you to go there and research some of those and see which ones might be visible to you. And that ends my my talk on how to get more familiar with the night sky.
Cool. Thank you very much, Tom. Okay, and we'll give it away to Alex.
Alrighty, so I'm going to talk to you guys today about exoplanets, one of my favorite subjects. And if you're not familiar with the term exoplanet, it's essentially just planets around other stars. So we're talking about other solar systems, some that you can see in the night sky. And I'm going to talk about how astronomers detect them. And let me just preface it by saying these objects are extremely difficult to detect. And the reason for that is because they're extremely far away from us. So, for instance, the closest, our nearest stellar neighbor is about 4 light years away. So that's the closest star to our solar system. And the other reason that it's really hard to detect exoplanets is that they all orbit really close to their stars typically. And here's my little demonstration before I go into my presentation. But stars are really bright. So that's my simulated star, and here's my simulated planet. And let's just go through my little cheesy presentation of the 3 different ways, the 3 main ways that scientists use to detect exoplanets. One that you might be familiar with is called when the planet goes in front of the star. So let's see. So you get a slight dimming. And the star dims by a very, very tiny amount, but with very sensitive instruments, we're able to detect that dimming and infer that there's a planet orbiting that star. Another way is the radial velocity method, where you can sort of see the star wobble. And I'll get into more about how we detect the star wobbling and how we figure out that planets are actually causing this to happen. And finally, there's a technique called direct imaging, where you actually, using what they call a coronagraph, you actually blot out some of the light from that star, revealing the planet. So this will all become clear in a second as I get into my presentation. Let me bring it up here. All right. Exoplanets. So I guess we can get into why exoplanets are important. Well, one reason that many people like to study exoplanets is because we're always on the search for the potential for life beyond Earth. So currently, believe that there's at least 1 planet or more around every star in the galaxy. Just for reference, the Milky Way is estimated to have about 200 to 400 billion stars. So you can imagine there's at least 200 to 400 billion planets in our galaxy alone. But what's even more amazing is that it's being discovered that many stars have been confirmed to have more than 1 planet orbiting them. So you can do the math. There might be on order of 1 trillion planets in our galaxy alone. And then if you go even further, there's trillions of galaxies in our universe. Also, there's a term, this is actually a pretty controversial term that I'll leave it to you guys to look into for yourselves, called the habitable zone. This is actually a zone defined around exoplanet host stars, where it's thought that the planet would have to be in that habitable zone in its orbit in order to have liquid water on its surface. So we're a little biased here as Earthlings, and the only way we know that life can survive is if there's water on your planet. So that's what we usually look for when we're looking for exoplanets. We want to see if there's water on the surface, and that gets us really excited because we think there might be a life, there's a potential for life there. And also I just threw in there, many exoplanet scientists are also looking for what they call exomoons, which are moons that are orbiting exoplanets, and there's potential for life on moons around in those systems as well. And then finally, exoplanets are important to study because they give us a chance to learn more about how our own solar system was formed, because we can look at other systems, and some systems have just been formed, or some systems are really mature, and we can try to find out how they relate to how our own solar system was formed. So here's the common detection methods. One is radial velocity. So that's the detection of the host star's red and blue shifting due to the gravitational pull of orbiting exoplanets, and I'll get into that more. But I like to think of this as measuring the star's wobble as a result of the planets pulling on it. There's the transit method, which is when the exoplanet actually passes in front of the host star from our perspective, and it dims very, very slightly. And then there's direct imaging. This is one of the coolest ones because you're actually taking a picture of the planet itself. So let's talk a little bit about radial velocity. So to understand radial velocity, you sort of have to understand that when 2 objects orbit each other, and I think this example is the Earth and the Sun. There's usually almost always a more massive object and a smaller object, and that smaller object actually has a gravitational tug on the bigger object as well. So it actually causes the object in the middle to appear that it's wobbling. but in reality, they're both orbiting a common center of gravity. And this is a good graphic that shows that. And in astronomy, we call that the barycenter. So I also wanted to include this. This is a cool video from actual data from the New Horizons mission. And in the middle there, that's actually Pluto, and that's its largest moon, Charon. And you can see that Pluto is not stationary. It appears to wobble because it's also orbiting its barycenter with Charon, or its common center of gravity. So moving forward, it's also important to understand for the radial velocity detection method that light has its own Doppler effect. So in sound, a lot of you are familiar with the Doppler effect with sound. If a car is going by you, it's going to go brrr when it's coming towards you, and when it's going away, it's going to go meow. It's going to go high pitch to low pitch when it's going away. Light has a similar effect, but instead of dealing with sound, when light is rushing away from you, the light that hits your eye is slightly redder, and when the light source is rushing towards you, the light is actually slightly bluer. This is only really noticeable by your eyeball if it was moving really, really fast. But with very sensitive instruments, we can see the small shifts that occur when something's happening, like a star's wobbling. So finally, if you understand those two concepts, here's a really cool animation that gives you a visual on how radial velocity detection method works. And so you can see that this is your simulated exoplanet, and there's your host star. And we actually we don't even need to look at the planet itself. We just look at the star, and looking at the star's spectra, we can see the spectral lines either red shifting or blue shifting. And the amount that it's red shifting or blue shifting tells us the exoplanet mass, and we can even figure out the exoplanet's orbital period and eccentricity, which is pretty amazing just by looking at the light coming off of that star. This is obviously a dramatic rendition. The shifting is extremely small, so you need very sensitive instruments to pick this up. Another method that's probably the most well-known in the public is the transit method. And this occurs when an exoplanet or a bunch of, a solar system full of exoplanets pass in front of their host star from our perspective, and we're able to see a slight dimming in that host star. So here's a nice little animation that shows the light curve dimming over time as an astronomer is observing the star. And of course, you don't get to see the actual planet passing in front of the star, but what your instrument does see is a dimming in the star. And this dimming is very small. We're talking about the total light from the star dimming by sometimes less than 2 or 1%. So yet again, you need a very sensitive instrument, but from this you can get the exoplanet radius, and you can also get the orbital period. So what's kind of cool is that if you combine the radial velocity method, where you get the exoplanet mass, and you combine the transit method, where you get the exoplanet radius, as a scientist, if you do both of those detections on a single exoplanet, you can start to infer things like density. So it's really amazing that just by looking at the changes in the light that are coming off of these exoplanet host stars, you can start to learn a lot of characteristics of the planets themselves without even looking at the planets. So it's kind of a cool form of science. The most famous transit detection observatory that you might be familiar with already is the Kepler Space Telescope. And I believe that the Space Telescope has finally ended its life, but over about a 6-year period, it constantly monitored 0.25% of the sky. And that patch of sky was right at the top of the Cygnus constellation, so very close to the plane of our own Milky Way galaxy. And it actually discovered it thinks it's detected over 3,000 exoplanets, but then every time Kepler detects a planet, the scientists have to go back and confirm that that detection wasn't a false positive. But there have been over 2,000 planets, I believe, that have been confirmed so far. It might even be more than that. I have to go look back at that data. But Kepler, all it was doing was looking for transits, so slight dimming of the stars. And it's pretty amazing in that small patch of sky how many were discovered in that short period of time. Finally, this is kind of the cutting edge of exoplanet research, direct detection. So actually using telescopes to image the planet itself. This is very difficult, as you could imagine. You typically need very big aperture telescopes, or you need to be very creative with how you take the picture. And one of the most common methods is to use what's called a coronagraph. And you can think of that, it's similar to if you go outside and you hold your thumb up and blot the sun out. That's a really simplified explanation, but you're actually trying to blot out the bright light from the host star, and then hopefully the planets come into focus. Don't be fooled. They don't look like the artist depictions of these planets. They're not these amazing pictures like we see of Earth from space. They literally look like dots. But it's very cool that you're able to actually directly image planets that are light years and light years away. And as our telescopes, our space telescopes and our ground-based observatories continue to get bigger and better, and our instruments get even more sensitive, I think we're going to see a lot more direct detection of exoplanets as we move forward in the future. So that's pretty cool. But right now we're limited to planets that are typically orbiting really, 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 really far away from their host stars. Okay, here's a few of my favorite exoplanet systems that you guys can go check out, read about it online. The Kepler-11 system. This is one of the most densely packed exoplanet systems out there. It's a confirmed system with 5 exoplanets. But here's our own solar system for scale. And you can see that all the Kepler planets are packed almost inside of where the orbit of Mercury would be. So they're all orbiting really fast and really close to their star. So it wouldn't be fun to live there. You'd be burning. Then there's Kepler-16b, which is often called the Tatooine planet. This is an exoplanet in a stable orbit around a binary star system. And I don't remember if there were multiples exoplanets found around binary stars, but I think this was the first one that was discovered to do this, and NASA made this nice, cool poster where your shadow always has company, because 2 stars means 2 different shadows, and then there's the classic picture from Star Wars. But what's interesting is that it's important to note that most stars that you can see in the night sky are actually binary or trinary or even more systems. It's more common for stars to orbit around each other as opposed to our own solar system with just 1 star. So I believe that most exoplanets are actually around multiple star systems, which is kind of interesting. And then finally, there's Kepler-22b. Ooh, whoops, I shouldn't say Tatooine, cross that out. An exoplanet only twice the size of Earth that may be a water ocean planet. So obviously, this is a big speculation, but the cool thing about this system is that it's close to Earth-sized, and it's in what scientists have deemed the habitable zone of this system. So I think that there's more spectra that has to be taken to confirm it, but it's believed that the whole planet could be a big ocean. So that's kind of interesting. That's a good candidate for life to have evolved. Finally, to end it off here, if you have an iPhone, I would really recommend downloading the Exoplanet app. As far as I can tell, it's free to download, and then there's some features you can unlock by paying, but the free features are awesome, and it constantly updates all the new exoplanets and gives you some really cool visualizations. And it even shows you how they were detected using the methods that we just talked about in this presentation. And I'll also put these, if you don't have an iPhone, these are great resources as well. A lot of researchers actually use these in their actual scientific papers. It's a great research that gives you all the up-to-date exoplanet information, and you can even take exoplanets and plot them according to their different characteristics, and you can come up with your own scientific conclusions based on that. So I'll post these links on the school or the class website. And then finally, here's another version, but this is just a catalog of planets that are only in their habitable zones. So this is just for people who are more interested in the planets that might support life. Thanks for watching.
Cool. Thanks, Alex. Let's see. We have about 16 minutes or so. Why don't I try and do a presentation, and then in the time remaining, we'll answer some more questions. So I want to talk a little bit about time here. So let me get my screen share up. Do my whole desktop, start to share, and play. Okay, how's that look? Is that up? I'll assume that's up. Okay, so the passions of astronomy are no less profound because they are not noisy. This is a quote out of a John Steinbeck novel, one of the few humorous political satires that Steinbeck did. And it tells the story of Pippin Heristal, who's an amateur astronomer, and by a twist of fate becomes King of France, because at least on one of his parents' side, he's got some long connection to King Charlemagne. So he is elevated to King of France, but he really dislikes it because he mixes his telescope so much. And so he will often try and sneak away on his motor scooter, as shown in the image there, to ride out to go take a look at his telescope. Eventually, he gets his wish, and he is removed from power as the King of France. And the whole story is about, Steinbeck's story is about that little adventure of Pippin. Check it out. It's a very short book. It's a great Steinbeck little read. So I want to talk about time. I just sort of like this art piece a bit because it gets across the point that we have time as told by the stars, and then we have time as we wish it to be on a clock. And the discrepancy, the challenge of keeping those two aligned has been with us for thousands of years and still is with us. And we're going to talk a little bit about that. So agricultural dependence means knowing when to plant the crops, when to pick the crops, when to expect the first frost. All this is fine. This is all driven by the sun, and you live your calendar off the sun. But as societies grow more complex, they typically want to have fixed dates for things like festivals, 4th of July, Christmas, your birthday, paying your taxes, whatever it may be. So you tend to want to have fixed dates. And this immediately introduces the difficulty of keeping the seasonal calendar, okay, what the sun says the time is, and the calendar years synchronized. And they will get out of sync here as we go along, and we'll talk about humanity's efforts to resync them and keep them synced, okay? So fixed dates, we want to have a fixed calendar. So what's a year? So just for reference as we go along, the seasonal year is defined as vernal equinox to vernal equinox. So that's spring equinox to spring equinox. And just, you don't have to remember this, I'm just saying it, is about 365 days, 5 hours, 48 minutes, 46 seconds, or 365.2422 days. And this is a shot of Salvador Dali's The Persistence of Memory with the melting clocks, and because we're going to be talking about clocks today. Okay. So yearly calendars, to start off, were often based on summer solstice to summer solstice, or when a particular star first rose with the sun, which was known as a heliacal rising. And so the Egyptians used Sirius, the brightest star in the sky, which rose in early July when the Nile was in flood. And within an economy that was based on the Nile floods, the heliacal rising of Sirius was the most important, and hence the first day of the year. So not January 1st, but sometime in summer, that became the first day of the year for the Egyptians. The image here shows if you were in Alexandria, Virginia in 2000 BC, and you can see the sun there on the yellow dot as it's just coming up over the horizontal line, show there on the horizon. And on the right side there of the image is constellation Canis Major, and the rising of Sirius with the sun. And so this is the heliacal rising of the sun. Okay. Now Sirius is the brightest star in the constellation Canis Major, and it's sometimes called the dog star because of that. And it's from the Egyptians' use of the heliacal rising of Sirius in early July. This is where we get the phrase, the dog days of summer. So that turn of phrase is quite old, and it goes back to our use of using stars that rise with the sun as the basis for our calendar. Okay. So that's one way to mark time within a year. We'll come back to that in a bit. But a year is a bit long. Societies tend to find that a bit long to use, so they want to break that up. And so how to mark time intervals within a year, no matter how you measure that year. So the first marker used was the moon, and that is the root word of the word month. Month and moon come together. And there are two main obstacles that cultures had to overcome to use the moon and to subdivide it within the year. The image here is the Aztec stone calendar, which was a lunar-based calendar. Okay. The first obstacle is that the lunar month varies. It's not constant. It varies between about 29 and 30 days. And this variance is caused by using the synodic periods. There's a new terminology for you, rather than the sidereal period. There's another piece of terminology for you. So the synodic period is the time between identical, what it looks like. So it's between identical sun, earth, moon, and object alignments. For example, full moon to full moon would be the synodic period. It's easily observable. You just go outside and look at the moon, but it's not so terribly useful because it does vary. The sidereal period is the time between identical star, earth, and object alignments, and this is the true period. This is the period that you would stick in Kepler's law or Newton's variation of Kepler's law. So it's the true period, but it's also harder to observe. And I want to walk a little bit through the difference between the synodic and the real period, sidereal period. So that's one way to remember which one is the true one, the one with real in the name. Okay, sidereal. All right. So let's start off here. We have the sun on the left. We have a distant star on the right. We have the moon-Earth system going around the sun. And I'm going to start my clock here when everybody is aligned. So the sun, the earth, the moon, the star, all aligned. Everybody's aligned. Now we're going to let time spin forward. The earth is going to go around the sun a little bit. Okay. And the moon will also spin around its time. So when you end up with the same earth, moon, star alignment, so everybody's in the same line, this is the real period. This is the sidereal period. Okay, and this is 27.322 days, and it does not vary. Okay, so this is the period you stick in Kepler's law, but it's not a full moon. In order to get back to the full moon, it's got to travel a little bit farther. Why? Because the Earth has moved around in its orbit. And so you have to wait a little bit longer for it to come back to a full moon again. And this is the synodic period, the 29 to 30 days. And it varies a little bit because the Earth, its orbit is not a perfect circle. It's slightly elliptical. And so in some cases it moves slower, some cases faster. And this is what ultimately gives rise to this variation in the synodic period. Okay, so there's a little bit of jargon for you, synodic and sidereal. So the second obstacle that cultures faced is that a year cannot be evenly divided by the average 29.5 day lunar month. 12 lunar months is 11 days too short. 13 lunar months is about 19 days too long. And so if you use a lunar calendar, your calendar will slowly but surely get out of step with the seasons. And so that ultimately, if you don't make any adjustments, then the hottest time of the year is going to end up being in what you call the winter months. And so many cultures got around this conflict by inserting an extra 13th month every few years or so. So they generally went short, okay, with 11 months. And then every once in a while, when it got a little too crazy, they would insert an extra month. And this is how they tied the seasonal year and the calendar years together. Okay, and just a little bit about the moon. So it was accepted practice in Babylon about 4,000 years ago that for a month, a full month after a wedding, the father's bride would supply his son-in-law with all the mead he could drink. Now, mead is a honey beer, and since the Babylonian calendar was lunar-based, this period after a wedding was also called the honey month, or what we call today the honeymoon. So again, this terminology that we use referencing time is actually quite old. The moon also gives us many other terms that we use. We have a lunatic, blue moon, a wet moon. We just went through a harvest moon. And so you've got all these terms associated with the moon. Okay. So I move forward in time, and the Egyptians gave up on using the moon to mark time within a year. And they took a much more radical approach to keeping the seasonal and calendar years together. They divided the year into 12 months, so this is where it comes from, of 30 days each for a total of 360 days. And at the end of every year, they added 5 days. for an approximation of 365 days. Now, they knew that 365 days was a little too short, and so they added extra days, were randomly added to keep the seasonal and calendar years synchronized. But it is from the Egyptians is where this idea of 12 months comes from for that. Okay. Fast forward, the Romans are now dominant world power. And originally they had an amazingly messy calendar. The year was 10 months long, with March being the first month of the year. Extra days were inserted at random at different locations throughout the Roman Empire to keep the seasonal and calendar years together. Okay. Some of the Roman calendar is still with us. In fact, as we'll see, quite a bit of it is. The Roman names of September, October, November, and December were from being the 7th, 8th, and 9th, and 10th months of the Roman calendar. So if you speak any, like if you speak Spanish or you speak any language like that, and you rattle off the numbers 7, 8, 9, 10, you can see the correlation between September, October, November, December being 7, 8, 9, 10, although they are not 7, 8, 9, 10 in our calendar. Okay, so this local-based calendar, 10 months, that was just 2 months, too much for Julius Caesar. So about a year before he died, he institutes a new calendar that we're going to have 12 equal months, so picking up from the Egyptians in that regard. March is still going to be the first month of the year, totaling 365 days. And then he standardizes when this extra day is going to be inserted. And so it's from Julius that we get the concept of a leap year. Every 4th year, or leap year, 1 extra day is going to be added at the end of the year. And this gave an average of 365.25 days, which is considerably closer than the previous estimates. And he institutes this across the entire Roman Empire. Okay. Now, Julius liked his new system so much that he decided to take a month and name it after himself. Okay. And this is where we get July. July comes from Julius Caesar, taking a name for himself. Money loves power, and power loves money. And one of the most richest families at the time in the Roman Empire was called the Juno family. They were big benefactors to Julius Caesar. And in a nod to his financial backing, Julius offered the Juno family a month of their own name. And this is where we get the term June from. So June and July are from Julius Caesar and his financial backers. So now the pattern is set, and every single emperor after Julius has to take a month and name it for himself. Fortunately, the vast majority of those did not stick. The only one that stuck was Julius's grandson, Augustus Caesar, and that is where we get the month of August from. So June, July, August, the summer months, are all from Julius and his grandson going through. So 365.25 days is a good approximation, but it's a little bit too long. It's about 11 minutes too short, but who's going to worry about 11 minutes? Well, after 130 years, that 11 minutes stretches into 1 day, and after 1,000 years, that stretches out into 1 week. But who's going to worry about 1,000 years? But 1,000 years does go by. And so by 1582, the seasonal and calendar years were about 10 days out of sync. And by this point, the Catholic Church is in power, and Pope Gregory. I want you to take a look at this calendar for 1582, in October of 1582. And what do you notice about that calendar? 1, 2, 3, 4, 15. Ah! So in order to resync the seasonal and calendar years, Pope Gregory just chops 10 days right out of the year. And this created near social panic, right? Like, what if my birthday was in there? I don't get my birthday. What if taxes? Do I have to pay taxes on days I were in there? And what do I get a wage if I didn't work in there? Near pandemonium breaks out. But eventually, you know, cooler heads prevail. They figured out, okay, nothing much, we just chop 10 days. So the first thing he does is he chopped 10 days out of the calendar. It's also from Pope Gregory is where the shift is made from March being the first month of the year to January. So January 1 is now made the beginning of the year because we can't have those pagan Roman traditions dictating first of the year. And he also picks up Julius's innovation of having a leap year every 4 years, and that is now added to February. So this is the root where we get leap years in February. So far he hasn't done anything. All he's done is shift the origin from March to January, and he's changed where you're going to add the extra day. So no actual new innovation here. But now he adds a twist. Century years that are divisible by 400 are also going to be leap years. So 1700, 1800, 1900, these are not evenly divisible by 400, and so they are not leap years. But 1600, 2000, Y2K are leap years. And so you get the extra day put in. And so this system is even more accurate. It's now only 38 seconds too short of what the sun says, or about 1 day in 2200 years. So what are we going to do? Are we going to wait 2200 years again and then go through an entire calendar change? Haven't we learned our lesson yet? We have. And so the modern year is 1 second is added to the calendar clock at midnight on either June 30th or December 31st, whenever the difference between the time that the sun says and what the clock says reaches 1 second. And so the calendar clock, what we say the time is maintained by the French using a worldwide network of atomic clocks. And the seasonal clock, which is based on Earth's rotation and the sun, is done in this relatively nondescript building that you see on the right here. This is at the U.S. Naval Observatory on the east coast of the U.S. Okay, so that's how we now sync our seasonal calendar and the other calendar. So how come there are 7 days in the week? All right, how come there's not 3, 2, 1, 19? Why are there 7? Okay, there are 7 days of the week because only 7 objects on the night sky were known to change their position on the celestial sphere: the sun, the moon, Mercury, Venus, Mars, Jupiter, and Saturn. And so our names for the 7 days of the week come from the Norse Celtic barbarians. So we have Sunday, that one should be obvious, Moon Day, Tuesday for Mars, Woon Day, Mercury, Thor Day, Jupiter, Thor being the god of Jupiter, Freya, the only female planet, the god of Venus there, Friday, Freya Day, and then Saturn Day, which is kind of obvious for Saturday. So even our names of the days of the week are rooted in time, and they stay around with us since antiquity. So finally, where did time zones come from? How'd that happen? Where'd that come from? Why did anybody come up with that? So the reason time zones were invented is because we started to travel, and in particular, it was done by the railroads. And so when you said that a train was going to leave at 1 o'clock or arrive at 1 o'clock, did that mean 1 o'clock from where the train left, or was it 1 o'clock in the city where it was coming in, and was that local 1 o'clock? Because time changes continuously as you move across. And so this just made the scheduling of trains just a mess. And so it was the train companies that instituted time zones in the United States, giving us the Eastern, the Central, Mountain, and Pacific. And that way, through entire blocks of the US, everybody had the same time, and then it would shift at definite boundaries. And so these were introduced in about 1883, and then by 1918, Congress made it law on time zones. And the idea was good enough that because of travel considerations mainly, that by the time of the forerunner of the United Nations made it law across the world. And of course, the time zones are not strict lines. You can see they bounce around depending on geopolitical realities that can change with time. So the time zones bounce around. But in essence, we got the time zones because of travel considerations. Okay, and that's what I wanted to say about time. Okay, so I went a few minutes over, but I think we'll be okay. Let's go 5 more minutes. So we'll, against my better judgment, we'll go 1 hour and 10 minutes. Let's go ahead and answer one more round of questions, and then we'll call it a day. Tom, Alex, do you see one you want to take?
I'll take the Mars one.
Okay.
Okay, there's a question about what our opinion about our civilization's ambitious planet to colonize Mars. Well, I think that's a good ambition to have. One day it would be really nice to have a group of humans living on Mars independently. And as you might have seen from news headlines, Elon Musk with his SpaceX company has plans to boost his rocket power to be able to reach Mars, and he is aiming for a first launch capability in about 10 years from now. So that's the goal. He might miss it a few years, but it's nice to see there's a goal. I'm sure there's lots we could learn on Mars. So it's always good to put humans on another planet just in case some big disaster happens here on Earth. So I'm all for it. That's my answer.
Okay.
Alex? Go.
Sure. So there was one question online that said, the gist of it was, how do you think life would manifest on other planets / galaxies? So I think this was a more abstract question, but I just wanted to address it because it's a really cool question that I think about a lot too. But I encourage you, if you're really interested on this stuff, to look up a field called astrobiology. It's kind of a budding field, and to be honest, a few years ago, not everyone took it as seriously. But now that exoplanets are being discovered, there's a whole field where biologists and astronomers are working together to try to understand how life might evolve on other planetary systems. And questions like, do you think that life even needs water to evolve like it does here on Earth? So it's really tricky field, and it's really tough to think about that stuff because we only have Earth's life to compare with how life exists. A lot of it ends up, unfortunately, being speculation, but you can put a real good scientific background into how you speculate those things. So it's really interesting. You can look it up. Check out astrobiology. All right, that's my answer.
Okay, and I'll take one more. Let's see, I'll take Cyril and Gay's question. If we assume the universe started with the Big Bang, what would have caused the explosion? Okay, a couple of points in there. So we don't have to assume that the universe started with a Big Bang. The observational evidence of that is overwhelming. And there's a number of lines of evidence on that, from you observe the expansion of the universe, so just run the movie backwards, the temperature, the current temperature of the universe, if you like, and the synthesis of hydrogen and helium, the amount that you get, all are very strong pieces of observational evidence that the Big Bang didn't happen, or did happen. You don't have to assume it. It really did. And it's not quite the right picture to think of it as an explosion. It's not like there was some pre-existing space that existed upon which the Big Bang did its act upon. The Big Bang is the expansion, the creation and expansion of space-time itself. And so it takes a little bit of thinking to get your head around, okay? But it's not a pre-existing space that then some explosion happens. Okay, even the concept of an explosion is not quite the right picture to have. on this expansion of space and time. Okay, and that will do for now. I apologize for not getting to every question, and I can see over on the YouTube that there are some other questions that we didn't quite get to. But if you post your questions in this thread on the discussion board, we'll answer them in text, and we'll go from there. So with that, I want to thank you very much for tuning in to this first YouTube live event. We'll do another one in about 3 weeks or so, and we'll go from there. So stay up with the course, do well, post your questions on the discussion board, and either Tom or Alex or I will pick up an answer. Okay, thank you very much for joining in. Bye-bye.